I know the coffee break is fun, but I'm going to be even more fun, so let's... The clock is ticking. That's it. Okay. So this is a little bit like yesterday. My task is to give you the basic of implicit solvent, and then Carl will go on more with the more specific application and construct that people have used, in particular on biomolecules. So implicit solvent perhaps is something that you've already heard about. Imagine you have a polypeptide here, a biomolecule, this unspecific green thing there, and it's in solution, so these are water molecules around it. So we know how to simulate that, but at the conceptual level, what's kind of interesting is to ask, is it possible to get rid of the solvent and still be rigorous? And what does it mean by getting rid of the solvent or integrating out the solvent? What do you mean by that, and how can you be rigorous about doing that? So imagine that I call all the degrees of freedom of the molecule here capital X. So these are all the Cartesian position of the atoms of the biomolecule, and capital Y is the degrees of freedom of the solvent, for example. So just, and so obviously the probability of any configuration of that system would be a normalized Boltzmann factor, P of X and Y. That would be, and then you would have to normalize it with respect to the position of the solute and the solvent. This total potential energy, U, it's trivial to write, should comprise a potential energy that depends only on the coordinates of the molecule of interest. There would be a potential energy function that tells you how the solvent molecule are talking together. And there's a coupling between the two, between the solute and the solvent, that depends on X and Y. Writing it like that actually presupposes that we're not dealing with many-body interactions and polarizable force fields and things like that. In spite of this, even in the case of polarizable force field, it would be possible to write formally something like that, where the coupling would be the subtraction of a kind of a super molecule and things like that. So this is not as restrictive as it may seem. So, but for now, imagine that this is not a there's no polarization, so there's no many-body coupling per se. So if you're interested in the average of any kind of observable that depends only on the polypeptide, so it's some observable Q that depends on the coordinate X, but nonetheless you have to average it over X and Y. This has to be there, and this would be your average. What we would like to have is a probability distribution that depends only on X, such that we get the same average. So this, I would call that like P bar of X, for example, or an effective probability that depends only on X. And of course, it's very trivial to imagine that, well, rigorously speaking, this P bar of X just has to be the P of X and Y where you have integrated out the Y. That's like totally trivial to write that, obviously. And once you've done that, once you would have, you know, your polypeptide submerged in some sort of influential thing such that you get the proper average by integrating over only the P bar of X. So how do we go about doing that? Well, the P bar of X, if we go back to the Boltzmann factor that we had before, is really this monstrous thing, is we integrate out the solvent degrees of freedom. So this is the normalization factor we had before, it's just except that I have written all the energy terms here specifically. And at the top, I have the P of X and Y, I'm integrating out the Y. So this is the integral over the Y solvent degrees of freedom. And this is all the stuff that goes in there. So obviously this U that depends only on X is inside the integral. It could be outside the integral, it doesn't matter. This guy depends only on Y, that matters. And this guy depends on X and Y, so that matters a lot because, in fact, I want to have a specific X here, and this specific X is here. So this coupling effect is really where this all comes about. Now, if I write this entire expression, by definition, I could say, oh, this P bar of X is probably, I might as well write it as a Boltzmann factor of some sort of effective potential, W of X over KT, and I can normalize it like that. So if I write this, then it would look as if there were never any wide degrees of freedom. You know, I would have like an effective energy. This is a Boltzmann factor. This is a normalization, and this is my probability distribution. So it's as if the wide degrees of freedom were never presented to you at all. So this W is the potential of mean force, the same potential of mean force, in fact, that appeared when you do the transition state theory of yesterday. And so the potential of mean force is really has to do with the equilibrium of degrees of freedom, physical degrees of freedom, and this is sometimes people refer to that as the free energy landscape. You know, so if you do a rate theory, very often you will want to have the potential of mean force along the reaction coordinate, or maybe along a pathway like Aaron Dinner talked about. If you want to talk about a polypeptide in solution, you would want to talk about the potential of mean force as a function of the conformation of the polypeptide. And if you want to do, for example, folding simulation, where the polypeptide is unfolded and then it refolds, then you would be moving on the free energy landscape of this potential of mean force of the peptide in solution. So people call it a potential of mean force, and I think I alluded to that yesterday, but the fact is that the derivative of the potential of mean force with respect to these x degrees of freedom is the average derivative of the potential energy, the microscopic potential energy, over the same degrees of freedom as you constrain the x. And so this is really just like the mean force, you know. And so if you integrate the first derivative of the potential of mean force like this, that's a kind of a reversible work, you can get the free energy difference, or the difference between potential and mean force at 2 points, just by integrating the mean force. So in principle, you know, if you want to have the value of the potential mean force between different points, you could integrate the mean force along a pathway in the x coordinate space. And sometimes people do that. For example, in the string method, they will compute the free energy along the pathway. But you can, your x1 and x2 are basically your own choosing here. So that's why potential of mean force is called potential of mean force. It's not an average potential energy. It's not an average. It's the integral. It's the work done by the mean force. Interestingly, though, the potential of mean force of a polypeptide in solution is also as a bit the form of a solvation free energy. It's sort of a configuration-dependent solvation free energy. So imagine you have your polypeptide in a fixed configuration, X, and it's in outer space, and then you carry it and you plunge it into the solution. Effectively, that's what you would be doing. You see, when you are in, let's see, let me try to gather my thoughts here, just a quick second. So this delta W is a solvation free energy. The W itself, of course, sorry about that, it contains, of course, the energy of the molecule itself. So if you have a fixed molecule in vacuum and you drag it into the solution, the free energy difference, the solvation, configuration-dependent solvation free energy of that thing will be the delta W. The delta W is everything that comes because of the solvation. The U itself is the internal energy of the peptide. So the delta W is like the solvent-induced influence on the PMF. It is like a solvation-free energy. And you can write it like that. So this is the same formula you would use to compute the solvation-free energy of a molecule, for example, because at the bottom, if you realize the coupling between the solute and the solvent is disappeared. We just have the integral over the solvent degrees of freedom. So it's a bit as if you have the pool of solvent without the peptide there. That's your reference state, and then you drag the peptide in there. That's what happens in the numerator. So it's like a solvation-free energy. This is all about equilibrium. There is no dynamics. But of course, what people like to do when they have a free energy surface, a free energy landscape, or a potential of mean force, is to imagine that there is also an effective dynamics in that subspace, this reduced subspace of degrees of freedom. And this is something that was really extremely popular. I mean, this kind of development, formal development occurred in the 1950s and 60s in large part by Swansig and Kubo and others, where they would write what they call the generalized Langevin equation. So this is, if you forget all that part here, basically this is Newton's law, you know, F equal ma, with a potential surface that is the potential of mean force. Now, if you just do that, that's a little ridiculous, but that's possible too. If you want to mimic not just the distribution causing, arising from this potential mean force, but you want also to mimic maybe the dynamics on that surface, it turns out that all these solvent degrees of freedom that you're integrating out would show up both as a dissipation. So this is the memory function that would dissipate. So this is opposing velocities. So this is like the friction. And there'd be random kicks coming from the solvent. So it's possible to justify this kind of generalized Langevin equation. And typically, the memory function, if you've chosen correctly the set of degrees of freedom to build your free energy surface, the memory function should actually be a function that sharply decays very fast over a short time. Like in this case was actually an ion in a Gram-Mesotine channel, so it decayed in about half a picosecond. Of course, if you try to do this, let's say, on all the carbon alpha of a polypeptide in solution, I bet you that many of these memory function on carbon alpha would not decay so fast, because some of the degree of freedom that you're integrating out, for example, would be maybe the side chains of the polypeptide. Now, if you want to do all the solvent is what you integrate out, and you keep all the atom of the polypeptide, you might have also some long-term memory effects, like, for example, if a water molecule gets trapped in a cavity. And so when you try to squeeze out the last water, that's a real structural effect, that comes from the granularity of water. And then treating water as a potential of mean force that can be integrated out like that will have some problem if, for example, the memory functions of these events or these kind of processes is long-lived and, as long time tails and things like that. In the best of world, you assume that this decays fast. You can even assume that this decays so fast it's almost like a delta function, and then you get just the Langevin equation. And then if you assume that the friction is so high compared to the inertial term, you can turn it into a kind of a Brownian dynamics. Sometimes people do that also. Notice that whatever is the dynamical model you do to propagate your system, whether this is the seemingly sophisticated generalized Langevin equation or the kind of apparently crude Brownian dynamics, your model, from the point of view of equilibrium, will not be better off, because in any case, if you use a potential of mean force here or here or here, the equilibrium that will arise from your simulation will be the same. So that's not influenced by the dynamics. The same way that a solvation-free energy can be decomposed into electrostatics and nonpolar forces, you can also decompose your potential of mean force in nonpolar electrostatics. When you do quantum mechanics, of course, you just have the Schrödinger equation, there's wave functions, and the only thing that is really there in the Hamiltonian is either nucleus-nucleus Coulomb repulsion or electron-electron repulsion, Coulombic also, or electron-nucleus attraction. So the only thing that's really there is a Coulomb law. But of course, quantum mechanics is not just about Coulomb's law. There is, Pauli's exclusion principle, you get van der Waals forces, all that thing. When you do a force field, when you go into molecular mechanics, these different physical effects that are all lumped together and blended together in quantum mechanics, of course you have different manifestation of that, and so it makes it easy and natural to talk about electrostatics and nonpolar forces. So, for example, the electrostatics would pertain to the interaction literally between the partial charges of the molecule together with the partial charge of the solvent. And the nonpolar term could be, for example, the Lennard-Jones part of the solute together with the Lennard-Jones of the solvent. So it's possible to see it like that. This decomposition is absolutely rigorous, that you can write in a biomolecular force field, you would have a nonpolar forces separate from the electrostatics. There's no coupling directly between the two in amber or charm or gromos or PLS. These things are separate. When I write a potential of mean force being like that, a sum of that, there's a little bit red flag that should go up in your head, because of course a free energy is not really, it's path dependent. It's like a thermodynamic process. And so it's not so simple to identify the nonpolar part with a nonpolar contribution here and electrostatic with that. And the way you have to do it is actually you have to imagine that this would be like a staging procedure. If you want to talk about the nonpolar contribution to the potential of a mean force, that would mean that you start from the pure solvent and then you turn on the nonpolar contribution in the influence of the solvent. So that's just the nonpolar part. When you want to talk about electrostatics, you would say, I start from the background of the solvent with the nonpolar contribution, and then you turn on the electrostatics while the nonpolar remains turned on. It makes no sense to turn on the electrostatic if there's no nonpolar. Imagine you turn on the charge on an atom, but there's no Lennard-Jones potential. I mean, the sun is going to crash on it. It's not even well defined. So when you write this kind of decomposition, it is path dependent, or it is an order. So it's a bit as if the electrostatic is a conditional free energy. It's conditional to the fact that we assume that the nonpolar was turned on during the entire process. The benefit of having the possibility of writing these potential mean force like that is that you can really then try to carry out all atom simulations about these components and then really probe and interrogate approximate models. Approximate models for the nonpolar part and approximate models for the electrostatic part, once you enter the world of implicit solvent, don't necessarily have the same mathematical nature. And if the only thing you can compare is the total, you don't really see where your model might need some tweaking or some improvement. If you can decompose it, it gives you a more incisive analysis of where these things are coming from. For example, electrostatics is perhaps where the cleanest arguments are possible. Imagine you have an ion in solution, but you'd like to get rid of the solvent and describe the solvent actually as a dielectric. Well, that's been done before. It was done almost 100 years ago, in fact. It's called the Bohr model of solvation, 1920. And it gives this formula. So it grows like the square of the charge of the ion, divided by the radius of the ion, and you get this 1 over dielectric constant of the solvent minus 1. What does it really mean, in fact? So the original derivation is actually a little weird because they even have a dielectric constant inside the ion, which in fact makes no difference whatsoever. But really the picture that comes from this kind of equation is that it's as if there is the dielectric of the solvent is like it's a bath of solvent, and there is really just a little spike of charge at the surface, at the dielectric boundary. And that spike of charge is, I put it negative here, I assume the ion is positive, so the spike of charge will be negative, and that's the reaction field charge. And it's a delta function that's really at the surface of the ion, at the surface. And it's proportional, it's linearly proportional to the charge of the ion. You can get that out of continuum electrostatics, but you can also get that from an analysis based on distribution functions. For example, this is the correct, this is the microscopic expression for the free energy of solvation of an ion. You have to charge up the ion, and then this is the free energy between the ion and the solvent. And this is the distribution function from the solvent. Now, we can compute that from simulation, and it's, for example, if you look at the distribution function around the potassium, this is what it looks like. It's a blue line. It'll be a negative spike. It happens that actually there's also a positive shoulder. Why is it so? Well, that's because the potassium attracts the oxygen of the water. So that's the negative spike. The position of the oxygen is this negative spike. And then the two hydrogens hanging out from the water gives you the positive bump there. If you have a chloride, you'll actually have a positive blip here that comes from the first hydrogen. There'll be a little negative blip coming from the oxygen, and there'll be a positive blip coming from the other hydrogen. And that's only the first shell, but of course this is a calculation that incorporates all the shells, okay? So obviously these functions are complicated. In fact, for potassium and chloride, they don't even look alike. What is the Bohr model doing? It's saying, well, this blue line actually is nearly like a delta function. And so I'm going to integrate out, I'm going to assume that it is such a sharp delta function, so hand waving a little bit here, that the 1 over r that's in this integral, I take it out, and I replace it by 1 over r ion, the radius of the ion. So I take it out. Once I have just that integral, so I've taken it out and I have the radius of the ion here. Once I've done that, I just have to integrate this. What is that quantity? Well, it is the charge coming from the solvent around an ion. Well, what is the charge? If I was very, very far away, I would have to obey Gauss's law. So the field would have to be Q of the ion divided by epsilon r. So that means that somewhere, there's some rule on how much charge there is in the solvent. If you integrate the whole thing, when you go far away, it's got to be equal to that. And so I know this value, I put it here, and now I have my integral of dq prime from 0 to q. It becomes 1/2 q squared. And so you've derived the Bohr model basically by actually identifying that it's a matter of telling that the charge distribution coming from the solvent, whatever its complex structure is to say it's almost like a delta function. So that's the assumption. It's saying that we're going to lump it into a single delta function like that. What also this shows is that, the definition of what is the radius r ion here and the value of the dielectric constant that we put here are sort of blended a bit together. If you made the radius of the ion that comes up here is some value that happens to fit somewhere in that complex shape. It's not necessarily a microscopic parameter. So you see that the radius of the ion depends a bit on the charge of the ion, for example. So that's that. Of course, the Bohr model, for example, can be tested. It's ridiculous, but it can be tested with even minuscule number of water. You could do a charging of an ion surrounded by 8 water, 20, 40, 120 waters, and then this is coming from free energy calculation. This is coming from just a Bohr model, and you can see it's definitely not exact, but it captures roughly the magnitude of the numbers that you expect. It's just almost embarrassing, but in fact it does, And the basis for that kind of Bohr model is where, when people want to use, for example, the Poisson-Boltzmann, the finite difference Poisson-Boltzmann on a full protein, really what we say is that, okay, now you don't have just an ion, you have a complex molecule, but there is a surface charge around that molecule. And the surface, so basically you have the molecule. If you look at this cartoon, you'd have the shape of the molecule, and inside there is the dielectric constant inside the molecule, and outside is dielectric constant epsilon 80. And there's a surface charge, there's a charge density in the solvent, but it happens to be mostly at the surface. And in continuum electrostatics, that would be the gradient of a kind of a step function that says when you're inside versus outside. The step function is equal, for example, to 1 inside the protein and 0 outside. So the gradient of that would be where the charge, the total charge density is located. It's at the interface. So if you write the exact formula that you would use if you ran explicit solvent simulation, what you will get is this. Here you would get the Coulomb's law, the sum over all the solute solvent charge. But that guy here is really just the average electric charge density from the solvent. And this dr 1 over r, that's basically the reaction field. That's the same that you would get in Poisson-Boltzmann. So you start to see where these two, the all-atom description blends in with these definitions, for example, of a continuum electrostatic. So that kind of identification can be done fairly clearly for electrostatics. It's not as clean for the nonpolar part. There are some very simple arguments about the nonpolar part. It has to be also, because the forces are very short range, it will also be something that's very close to the surface of the peptide, and sometimes the nonpolar part is represented as being proportional to the exposed solvent area. But there are people who have counter arguments or criticism of these kind of models as well. Now, of course, the continuum electrostatics model is not just about the solvation of a polypeptide. Imagine you have two parts that are separated. Like you could have two ions that are separated. If they're far away, you would say, well, this should be the charge of this guy times the charge of this guy divided by epsilon r. That would be the continuum electrostatic description of that interaction. But already you can see that this can have some limitation, because if you have two ions in water, only when they're separated maybe by 5 to 10 angstrom can you start to look at the 1 over R, laws. But once you start to get closer and closer, you get these kind of structural effects. These are like when you start to penetrate the first hydration shell of each ions, the potential of mean force between two ions will not be just a plain continuum electrostatics. And so definitely one has to be very careful in using just these simplified models and believing all the fine-grained detail about that. So I think that's my last slide there. So any questions at this point, or? Yes. Oh, the salt effect. So that leads you to the Poisson-Boltzmann equation. That would be a kind of then there would be a screening, not only a dielectric constant, but there'd be a screening. Interesting, if you allow me, just one thing, if I go back to this guy, yeah. So these kind of arguments tell you where to put the boundary for the dielectric. So when you construct a Poisson-Boltzmann model, you have to see where the epsilon is 80 and where the epsilon is not 80. And typically you can have these atomic models, and the radii are essentially semi-empirical parameters that you have to fit to make the system work well. The radius for the dielectric does not have to be the same radius as for the counter ions. As weird as it may seem, it's easy to make a model where there's only the radius of the atom, and then the epsilon on the other side is 80, and the kappa is, the Debye screening factor is not 0. But it's actually not true. You could say that, the water around this, and you could verify that with the explicit atom simulation, that the water around this is actually hydrating this group very well, and if there are counter ions here, they can't really penetrate there. There's like another radius. So it's possible that the radius of these ionic screening effects should not be the same. It does not really change, no. The epsilon is still a scalar in this particular thing. It's still a scalar, but it's mostly, I think in the language of ionic screening, that would be more like a kind of semi-Stern layer or things like that, where you really have not necessarily an exact matching of dielectric and ionic configurations. So you have to be careful. Yep. This is true. Absolutely. And it's also, from the point of view of free energy, it's easy to run a simulation where you couple a molecule to the solvent with a lambda. You could do the same thing with coupling a molecule to an ionic soup, an electrolyte solution. And then you could compare numerically what the free energy is giving you with that. But it's not so easy in simulation to vary continuously the concentration. Because you actually enumerate how many ions you put in the system. So you can't continuously vary the concentration in the simulation, not so easily. Any more questions? Yeah?
Just to be kind of sure from your last slide, I think what you're saying is ions coming together, you don't want to use implicit solvation to study.
Well, I don't know what the take-home message is about that slide. Is mostly you could take an implicit solvent model that is first and foremost a continuum electrostatic model, and then maybe decorate it with short-range wiggles. So when, let's say an aspartic acid comes close to a lysine, that, yes, when they're 10 angstrom apart, it's like continuum, but you have actually tabulated, for example, the wiggles so that actually you simulate the wiggles correctly. And you could tabulate that kind of thing. I mean, you could compare, all the positive type of side chains like arginine, lysine, histidine coming close to aspartic or glutamic acid, and then tabulate those for better or for worse. It's not impossible. You could do that. We actually have done that when we do a Brownian dynamics simulation of ion channels, for example. We throw away the solvent. We keep only explicitly the ions, and the ions are interacting together with a Coulomb law. but also with the wiggles. And so when the potassium and sodium are getting close together, they form ion pairs, and the wiggles are there. And the wiggles were fitted with spline tables to match, for example, all-atom simulation. So it's possible to do that. You may want to put this on your pocket.